Good afternoon. I am Mr. Ish. You are joining me for this video. I promise you it will be a beneficial video. A good derivation video here. Sine x, cosine x. We know in terms of derivatives these are very easy. But how do you actually arrive at that easy derivative? We will look at here firstly using a graphic approach and then the limit approach, which is the basic definition of a derivative. You want to look at the graphic approach for this derivation first because it leads to an assumption which very well plays into this. You know and remember, derivative of sine x equals cosine x. We'll show you why that is the case. And the derivative of cosine x is equal to minus sine x. Again, we'll show you each of these using these two approaches. This first and this second. Sine x graphic approach, not difficult. Think about the sine x and plot all the landmarks. We'll look at a limited domain here from 0 to 2 pi because it's an infinite domain curve. You only need to look at a limited domain and you can extrapolate the derivative from that. Sine of 0 is always equal to 0. Sine of pi over 2 is equal to 1. Sine of pi is a 0. Sine of 3 pi over 2 is a minus 1. Sine of 2 pi is a 0. Connect your dots. You know how to do the basic sine curve here. Well, I really missed the dot, but we have the sine curve. At each of these points, at the termination, just do a dotted line ahead just to show that it was continuing onwards. At each of these points over here, determine what would be a good tangent line slope. If you were looking at this point and you want to determine a slope of a tangent line, you would actually draw a tangent line along this and you would graze it, and you know the slope of this tangent line would roughly equal 1. Because it has an equal inclination in terms of steepness and flatness, it's equal to a positive 1. So at 0.0 x-axis domain value of 0, we've established a slope over here to be equal to a 1. At pi over 2, if you were to draw a tangent line, it would be a flat line having a slope of equal to 0. Remember this right here is a graphic approach. At pi over 2 x value, we develop a slope of a tangent line that's 0. At pi, you draw a tangent line and it's pointing downwards, equally flat, equally steep, but a slope here is going to be a minus 1. So at pi, we're seeing a slope of a tangent line equal to minus 1. Let these be my domain values and let these be the resulting slopes of the tangent lines designated here in terms of the y coordinate. At 3 pi over 2, a slope of a tangent line is always flat and equals 0. So let's put that here. 3 pi over 2, we have a slope of a tangent line that's 0. And lastly, at 2 pi, you draw a tangent line. It's going upwards, positive 1 slope. And we can add that 2 pi having a slope of a tangent line of 1. We have these coordinates made, and let's make a new plot over here. Utilizing these coordinates, we draw a new plot, and that right there will be the resulting graph, but the graph of a derivative of sine x. At 0, we have a value of 1. At pi over 2, we have a value of a 0. At pi, we have a value of a minus 1. At 3 pi over 2, we have a value of a 0, and at 2 pi, we have a value of a 1. Connect these. I'm not showing you the domain values. Continue this here, continue this here. When you look at this, you know this is pi over 2, this right here is a pi, 0, 3 pi over 2, and 2 pi. What are you seeing over here? You're seeing the basic curve, this cosine curve. So now we've established graphically that the derivative of sine x is equal to cosine x using this procedure here. And it's not hard, and you've proven the derivation procedure, but graphically using your domain points and the slopes of the tangent lines at those points. We will do a similar presentation here for the cosine x. Alright, cosine x. When you're actually plotting this basic function, right, this is my basic function for which we have to determine the derivative. Cosine of 0 is always equal to 1, cosine of 90 is a 0. Cosine of pi is a minus 1, cosine of 3 pi over 2 is a 0, and cosine of a 2 pi is a 1. You connect these and you get your basic cosine function curve, and let's continue this onwards. When you do the derivative determination, you're again finding the derivatives by finding the slopes of the tangent lines at these domain points. At this point right here, a tangent line would obviously have a slope of 0. We won't write the points out here, we'll just look at everything directly off this graph. At 90 degrees, you have a downward sloping tangent line. Slope here would be equal to a minus 1. At this point, pi, we'll have a flat tangent line, slope of a 0. At 3 pi over 2, we'll have an upward facing tangent line. Slope is equal to positive 1. And at 2 pi, we'll have a slope which is equal to 0 for that tangent line. We have all of these points. All we gotta do is graph them based on the points we've established. It'll never go higher than 1. It'll never go lower than minus 1. what we can do this time is write these key points out over here, and then we'll plot our points. At point 0, we had a slope value of 0, so let's put that 0, comma 0. At point pi over 2, we had a minus 1. Pi over 2, we have a minus 1. At point pi, we had a slope of 0, so let's put that here. At point 3 pi over 2, we had a slope of positive 1. We'll put that right here. And at 2 pi, we had a slope of 0. Connect these dots, alright? I'm seeing a curve which is coming out like this, and let's continue this onwards. Now this is not really a sine x curve, because a sine x curve would be like this, and that's my dotted curve right over here. You know, the sine x curve would be this dotted curve as you're seeing over here. But what we are seeing over here is a reflection of the sine x curve, the basic sine curve, but across the x-axis, and that right there is why the derivative of the cosine x is not a positive sine x, but it's a negative sine x, because this graphic derivation procedure leads you to have a negative sine x in terms of a graph that is a reflection of a original sine x but across the x-axis, and that right there is why this is the case that it is. What remains now is for us to look at these derivation procedures for both of these, but using the basic definition of derivative, which the good reason why we have shown you the graphic procedure, because in those you'll have to know that the sine x led to a cosine x and the cosine x led to a minus sine x in terms of the derivation. Let your original function be sine x, and we have to determine the derivative of this function. We'll use a basic definition of a derivative, and it will proceed in the following manner. Limit as h approaches 0, you have f of x plus h minus f of x over h. You'll have f of x plus h minus f of x over h. We have to remember this formula. It's something you don't want to take for granted. You plug this function in regards to that. Sine x plus h minus sine x all over h. I should have the limit designation over here, limit as h approaches 0. You have to use the sum and difference rule for sine to open that up. You'll have limit as h approaches 0 sine x cosine h plus sine h cosine x minus sine x all over h. Remember that identity, you have to bring that identity into play. The sum difference formula for sine. When you see all of this, you see a commonality develop right over here, and we'll use that. Limit as h approaches 0. I'm going to bring this with that. I have a sine x cosine h minus sine x all over h, and then I have this plus sign. I'll create a new limit using the limit property across a positive sign, the sum property of limits. I'll rewrite cosine x first, and then I'll put sine h over h. I'll separate everything here cleanly, and I'm going to isolate this sine x from right here. I'll have limit as h approaches 0. I have separated sine x from here, and that leads me to have cosine h minus 1 over h. Remember, this is not hyperbolic cosine, this is cosine of the value h. Plus limit as h approaches 0, we have cosine x and then sine h over h. If you look at this and you plug in zeros, what you end up getting is a cosine 0 minus 1 over 0. You have an indeterminate limit form of 0 over 0 developing. If you look right over here at this part here, and you put 0 in place of h's, you'll have a sine 0 over 0. You'll have again an indeterminate limit form develop 0 over 0, for which you can do the L'Hopital's rule procedure. Let's rewrite everything here in a good format, and let me erase this extra writing over here. Limit as h approaches 0, I have sine x. The product of a limit is equal to the individual limits of all the products that are involved, times limit h approaching 0, I have all of this, cosine h minus 1 over h, plus, I'm going to separate this into its separate limits. These are all the steps you have to take because they simplify the procedure. Times limit h approaching 0, we have this part right here, sine h over h. We've already established these are indeterminate limit forms, for which you would do the L'Hopital's rule procedure. You would do the derivative of the numerator, you'll do the derivative of the denominator. If you did the derivative of the numerator using the graphic assumption approach for derivation, you know cosine h will give you a sine h, right? It will give you a minus sine h actually. And in terms of the derivative, 1 is a 0. In terms of h, it will be a 1. You could plug in 0, you'll do a minus sign of 0, you'll get a 0. All of this right here will boil down to a 0. If you did the L'Hopital's rule procedure here, because again it's an indeterminate form, you can do sine of 0 divided by sine of 0, you'll get 0 over 0, but then you can do the derivative of the numerator, derivative of the denominator, you'll get cosine of h over 1, and you can plug in 0, and you'll get a 1 over here. Think about it, cosine of 0 is a 1. All of this boils down to a 0, all of this boils down to a 1. When this 0 hits this sine x limit with it, all of this gets zeroed out. You don't even have to look at that anymore. But when this 1 hits with this cosine x, it doesn't zero anything out. Limit as h approaches 0, cosine x is just equal to cosine x times this 1, and your resulting derivative is cosine x, and you're done. So if f of x is equal to sine x, then the derivative of sine x must be cosine x through this procedure that we've shown you right here, using the basic definition of a derivative, and this setup and this procedure has been solved. We'll end this video here with this derivation procedure for cosine x. We already know cosine x equals minus sine x. We have to use this basic definition of a derivative to show you that is the case. Limit as h approaches 0, we're looking at the derivative of this. You'll put everything into that basic definition of a derivative formula you know. You do cosine x plus h minus f of x, which is cosine x all over h. Not a difficult procedure, but you have to remember the trigonometric identity for this. The sum difference formula for cosine x. You know that's going to be limit as h approaches 0, you'll do cosine of x, cosine of h, minus sine of x, sine of h. Nothing hyperbolic over here. Minus this f of x, which is cosine x, all over h. And that right there is this part right here expanded out. Look for a commonality. I see one here, I see one here in terms of the cosine x. Limit as h approaches 0, we combine those common terms. We have cosine x, cosine h, minus that cosine x all over h, minus. See this minus? Now I'm creating a new limit using the difference properties of limits. I have a sine of x and then I have a sine of h. These are angles x and angles h, which are being impacted by the sine and the cosine functions. Here I can isolate a cosine x. Limit h approaching 0, I isolate this cosine x and I parenthesize what remains. And you've seen this. Limit h approaches 0 here, I don't isolate anything because there's nothing to isolate, but I can bring the denominator under this. I'll again create new limits based on these products of these functions I'm seeing right over here. And again, everything will follow a similar path as the previous one. I have a limit creating over here, the product property of limits, cosine of angle h minus 1 over h, minus limit as h approaches 0, I have sine x, times limit as h approaches 0, I have sine of angle h over h. If you were to quickly put 0 here in places of the h values, you'll again see the indeterminate form show 0 over 0, and again over here 0 over 0. Remember the forms positive minus infinity over the same, 0 over 0, 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. And you also have infinity minus infinity, and you have also 0 times infinity. These are the various indeterminate limit forms, and I've presented videos on all of these, how you challenge those, how you channel those through in terms of your work. Well, we're seeing that come into play over here, so you have to use the L'Hopital's rule for limit determinations for these parts which develop these forms, which is of course this part right over here and this part right here. Very quickly, if you were to do the derivative of the numerator and denominator, cosine h would give you a minus sine of h. 1 will come out as 0, h will come out as a 1, and you could put in 0. When you do this, you're basically ending up with a 0, right? Because sine of 0 is a 0, 0 over 1 is legitimate and it's equal to 0. When you do the derivative procedure here in the numerator, you get a cosine of angle h over 1. You can put in that 0, you do cosine of 0, you get a 1. All of this boils down to a 0. That 0 will multiply with this and it'll zero everything out right over here. All of this right here boils down to a 1, and that 1 will multiply with this sine x, so nothing will get neutralized, so we can continue from this point onwards. So let's erase this and continue this part of the expression. I have a minus, limit as h approaches 0, sine x will equal to sine x. Because what have you really done? You're looking at a, let's just say a hypothetical function. Here was my x, you were h units away here, x plus h. all you've done is now you've reduced this delta x or delta h to 0. You've essentially come from your second point all the way up to your first point, a coincident point. Hence, limit h approaches 0, you're ending up with some point further away to your point of interest right on it. So sine x is equal to sine x because that's the point you're looking at. When you look across here on your y value, whatever that value is in terms of the range, that is your sine x, which is why this stays as is. This here is equal to 1 as I showed you, and you get a minus sine x, and your derivation procedure is done. So f of x is cosine x, the derivative of that must be minus sine x, and you're done. So again, remember everything you saw over here graphically and using the basic definition of derivatives for both sine and cosine x. These are very easy template derivatives, almost too easy that sometimes one never bothers understanding or looking at the derivation procedure behind them. The graphic derivation procedure is legitimate, and this basic definition of a derivative using the limit approach is also legitimate. Both approaches you should be aware of and you should know. And with that, we end this video. I hope you enjoyed this video. Thank you for watching. Stay tuned. Have a nice day.